Welcome back to another lecture of E2080 Microprocessor Systems Design and Interfacing course. So last lecture was in fact sort of revisit of our 8-bit microcomputer, and then we slowly discussed about generalization of some of the units, had a glimpse of each one of them separately from an architectural point of view. And then we also had a tutorial on how a memory map is made for a microprocessor. So you might have got the feel that there are different kinds of memories. There are RAMs, there are EPROMs, and so on, and they all are physically located at different places on the chip. But then you arrange them in such a way that virtually that they form a continuous address, and it looks like the entire thing is a one chunk of memory for the microprocessor. And then you continuously issue the address from the perspective of a microprocessor. So even though they are located different places, they may form different types of memory. For a microprocessor, it appears to be like one chunk of memory. So that is something which is very important for a modern day microprocessor, which we typically known as memory map. Okay, so we build some more base towards the Cortex-M plus processor, which we will be taking in detail in near future, maybe next week. But some more things to be bridged for you. So this is more of that sort of a lecture. So let's start without any further delay. Okay, so again, I keep on repeating these things many times because we do have a tendency that we see and then we forget. But if we see many times, we may have a permanent embedding in our brain, right? So this is one thing I always try to do that, even myself, keep revisiting it. So this is again the viewpoint that should be there embedded in your mind by now. So we do have a processing unit, a microprocessor, which will have essentially ALUs, registers along with the control unit. So registers as the temporary memory for the ALU, and then there is a memory which is actually where you store the instructions, the data, and of course the control logic, you would say. And then they are interconnected through buses, right? So the entire concept is nothing but, as Alan Turing dreamed a long back, it is a memory driven hardware. So you change the memory, you change the way the hardware is going to behave. Okay, so that's the beauty about this concept. So it's a stored program device. So don't mistake or don't get confused by what it means. It is a stored program device. You change the program, you change the functionality of the device. Okay, so as I think this part I discussed some time back also, maybe during the introduction lectures, where there is a beautiful handshaking happening between the software and hardware of a microprocessor. In fact, that is why I think many times I can reiterated, sorry for boring, that maybe Apple systems are so powerful because there's a beautiful handshake between the hardware and the software. Okay, so yeah, I don't know from where to where we go, let's start from the top. Okay, so we do have some thought, we want to make it work, so we write a program, and that program is written in a very high level language like MATLAB or Python or maybe C, and that is governed by your operating system, right? OS. And of course operating system will have a compiler or a translator which will convert this high level language into a low level language like assembly language. So that is what the first step. Sometimes this may not be there, it may be directly given to an compiler / assembler, and you have the machine language or the machine opcodes in place. So these are nothing but sort of zeros and ones, right, that we talk about. So high level language to assembly language to the low level language, I think should be very clear to you by now. And then of course we do call a lot of library functions which make our life easier when we write a program, and those library functions are always converted to the machine language at some place, and they will be linked along with our original code using a linker. Okay, so the functionality is like you link your library functions along with our main code, and that's it. So that is where the software part ends. Okay, and then of course this has to be executed on a computer, a microprocessor architecture, and if you dig deep down on the microprocessor architecture, you will end up in getting those building blocks, the ALUs, the RAM, the chips, the interfaces, everything. And then further, if you dig down each of these circuits, you will end up in getting elementary logic gates. Okay, so there is a beautiful claim in this website. This is actually a very interesting course, similar to our 8-bit microcomputer, where they build a very fancy computer system out of NAND gates. Okay, so that what they are saying is like NAND gate is a basic gate, and I can literally construct any circuit, digital circuit, any logic circuit using NAND gates. And of course, once you make logic circuits, you can always make the blocks like CPU, RAM, etc., like what you did in your experiment 1. And then of course, using that you make your microprocessor. And once microprocessor is ready, all you need to do is appropriate instructions have to be made so that you can make use of this hardware. So this beautiful software hardware handshake is what you will study in this course, right? Okay, so move on. This is what, again, if somebody is still confused between what is high level language, assembly language, machine language, etc., this slide literally tells you that. So you can write a code. In this case, I am adding 2 numbers. This is what you do in C++. Okay, so very simple, right? And then of course you can do, if you do a compiler, it may get converted to an assembly language like this. Okay, so you may be able to make sense out of some of these commands by now. Okay, and then of course this machine doesn't understand, so machine only understands only in this terms. Okay, so this is what we call as machine language, and this may be something like exe for Windows or ASM for something like ARM processors or the microprocessor level, or it can be bin file, something like that. Okay, or depending on your operating system, it may appear to be something else. Okay, so move on. So that's it, high level language to instruction set to mnemonic opcode set. So even in this course, even if we are treating Cortex-M0 plus, what we will do is we will start at this level. Okay, so we will start with this and then we will slowly move to something like C. Okay, so that's a path we will also follow. So you will start coding with the instruction set, basically the assembly language, and then once you are comfortable with that, probably we will shift to C or C language. Okay, so very important. Now we are actually going into the crux of this course. So we are going to talk about Cortex-M0 plus. So Cortex-M0 plus is what you are going to study in detail. So that is actually manufactured by ARM, or in fact not manufactured by, but sort of licensed by ARM. So ARM is nothing but advanced RISC machine. So you don't know what is RISC yet, reduced instruction set computer. We will discuss that in some detail in some of these slides coming forward. But ARM, it's very important because Cortex-M0 plus is actually something which is a baby of ARM. So you should know more about ARM, its significance. And then of course it is a 32-bit microcontroller unit or microprocessor unit. So why 32-bit microprocessor unit? Because if you take any traditional microprocessor course, they all do with 8085 or 8051 or 8086 and so on. Those are 8-bit microprocessors. But in this course, we are not even talking about 8-bit, we are talking about 32-bit, and you could ask me that question now, why it is so. So next few slides will answer that for you. Okay. So growth of computers, it's extremely important for you to understand, right? So this is something which is very representative. Okay. So initial days you had those mainframe computers where something like so let's say some plot of number of people per computer. So it was like 1 per enterprise. For a company, you had a machine, something like that. Then you had a workstation or mini computer. Mini computer may be 1 per company, and then workstation it may be 1 per engineer. Personal computer 1 per family maybe, so number of people got increased. Laptop 1 per professional. Smartphone 1 per person. Okay, so it became so, and now you have so many smart sensors which themselves are a microcontroller unit for controlling, and that is like 100 to 1000 of them per person. Okay, so that's the density that you could actually imagine. So basically this is really staggering growth that you could actually envision over the years, and we are almost like 2021 now, right? So you can only expect maybe 100 to 1000 going to something like 10,000 sensors per person in near future, because IoT is all about that, right? You mount so many sensors on everything that you can think of. There is another way to look at it, is something like how much the size has reduced. So there's a beautiful paper from Nagawa. So if you Nakagawa, if you are very keen, please look into it. So he predicted, or in fact not prediction, he estimated that there's something like 100x size reduction per every decade of our years. Okay, so you can actually think of That's very interesting, right? So you can actually see that the size getting reduced from occupying something like a floor to a room to something like a half of a room, and then of course a desk, and then of course on your palm or lap, and then of course to your finger, and maybe now on fingernail you can say. So that is the way it is actually going down. Okay, so there's a size. So basically everything has to be miniaturized. You know that this is achievable because of the reduction in the size of transducers and more transducers per unit area governed by Moore's law and so on. So all these have contributed to the size reduction. So this is something which is also worth noticing. Another aspect is the pricing, right? So the price has also come down drastically, that you can actually think of literally maybe paisa sending on for processing. So another interesting is the application side, right? Earlier the application was all on number crunching or data storage. It was the primary aim. Then it became productivity and interactivity. User interface became so popular with the Windows and all those things later, right? And then of course the recent trend is all about sensors, right? The interconnectivity, the networking aspect. So all those things came into picture. You are worried about streaming nowadays, right? You're not even worried about working on a particular computer, the speed of that computer. Yes, you are worried about how that computer communicates with your internet, right? So all these things have actually put a lot of pressure on those who are working in the computing field to come up with processors which are low power, which could actually be put into smaller footprint, which is low cost. So all these things are very, very important, and those things actually driven the progress of microprocessors from 4 bits to 8 bits to 32 bits, and then at the same time the 32 bits should not be occupying a lot of area and a lot of power. So we will see that as we go along, what are the features that is there in the Cortex-M0 Plus, for example, which will enable all these things possible. Okay. So 32-bit microcontrollers is very important. Why it is so important? So this is a trend. It is comparison between programmable logic devices like FPGAs against 32-bit microcontroller unit over different years. So this is still 2012. So you can extrapolate this probably, because you are engineers and you know what is, if you know the trend, you can actually extrapolate what is going to happen, right? So it's very clear. So there is definite increase in the microcontrollers preferred over programmable logic devices. One of the main reasons is what we saw in the previous chart, the shrinkage of size and power. Okay, because programmable logic devices are by design power hungry, whereas the microcontroller units are not by very power hungry by design. Okay. Of course, the functionality aspect, maybe the speed of operation may be much better in the case of programmable logic device, but it is a trade-off. And then of course microcontrollers win. And when you want higher speed, that means you need to have higher number of operations per second at pretty good accuracy. In that case 32-bit is the choice for you, because 8-bit means if you want to do some operation on 32 bits, you need to do it 4 times, right? So 4 cycles are required for even doing it using 8-bit. So that is all avoided when you have a 32-bit case. And also higher the number of bits, better is the accuracy. Why? Because a higher number of levels or higher number of or resolution is better in the case of a 32-bit microcontroller compared to 8-bit microcontroller. Maybe I think you are not studied about that. So let me quickly brief about why the accuracy, slight off bit, but it's very important to know. So why 32-bit is more accurate than 8-bit. Okay. So let's say, so I have a waveform, some analog waveform. Okay. So when I say it is 8-bit, so this is analog, so I need to convert it to digital. So there is of course discretization in time and discretization in amplitude. And when we talk about bits, it's all about discretization in the amplitude. So let's say 8-bit. Okay, so 8-bit literally means you have 2 raised to 8, because 8 bits, that means 2 raised to 8 combinations are possible. So this is something like 128 in this, like 256, right? Yeah, 256 is what you get. So literally this means this waveform is actually getting divided into 256 levels. So this is entire dynamic range of the waveform. This you are going to divide into smaller groups, and each one, okay, it is something literally like let's say V is your original range, total range. This is V up, and then you are dividing it by 256. So delta V is given by this, and this is actually delta V. So the resolution is like V by 256. Now imagine you have 32 bit. So 2 raised to 32, I'm not going to calculate what that is. That is like, we can say something like 2 raised to so many. It's some very high number, right? So that is something like V by 2 raised to 32. So you can see that the number of levels is so much, right? You are going to divide V by 2 raised to 32, that the resolution is so much, and then of course the approximation to a particular value is the error due to that is very less in the case of 32 bit compared to 8 bit. So that's why we call that is better accurate than. So you can think that one number being represented in 8 bit and 32 bit, right? 32 bit has so many provisions, so even some small change is captured very nicely in the case of 32 bit compared to 8 bit. Okay, so I hope I'm able to convey that point clear. Okay, so moving on, and another interesting comparison. So 32 bit against other microcontroller units like 4 bit, 8 bit, 16 bit and 32 bit. And we can see over the years, this is still 2017, and this is a growth percentage if you want to compare. So you can actually see, in fact, the 4-bit microcontrollers have gone out of scope nowadays. Nobody is using. 8-bit microcontroller, there is a steady increase. That is good. And then of course, the 16-bit seems to be very less growth, and 32-bit is almost the winner. Okay, so why 16-bit is because the difference between 8-bit and 16-bit is not much compared to 8-bit and 32-bit. Okay, so 32-bit gives you much better accuracy, and there was a lot of focus from companies like ARM on 32-bit microcontroller units at low cost and low power, and that is the reason why they became so popular compared to 16-bit microcontroller unit. So if you go for any commercial industrial applications, you would either see 32-bit microcontroller units a lot, or you would see 8-bit microcontroller unit. It's a domination between these two. And since 32-bit is more interesting, more accurate and more contemporary, our course is focused on a 32-bit microcontroller unit, which is the Cortex-M0 Plus. Okay, so I hope I'm able to motivate you enough. Okay, now having said that, now why study the ARM architecture is still an unanswered question, and why Cortex-M0 Plus in particular is even more interesting question for you to know. Okay, so let's move on. So lots of manufacturers ship ARM products. So that is, I think sometime back I told ARM is like Uber or the Airbnb or something like that. So Uber doesn't own a single car, right? Ola or Uber doesn't own a single car, but they are the largest taxi service, you can say. Similarly, Airbnb, I don't know how many of you heard about Airbnb, is a hotel service, but they don't actually own a single hotel. It's similar to this one. Even the, I think something similar is also there, Oyo rooms or something like that, right? So it's also similar concept. So similar to that, ARM doesn't manufacture any microprocessor or microcontroller, but they do make designs, digital designs, and then of course all the things they license to all these companies listed over here. I don't know how many of these companies are known to you. Probably NXP is known to you. We are using one of their boards. Texas Instruments should be popular to you. ST Microelectronics is something which is popular. Atmel, I'm sure you might have heard. Cypress Semiconductors. So this is only a sub list, by the way, right? So but all these companies actually manufacture ARM processors. Okay, so it's very popular if you want to think that way. So let me ignore all erase. Yeah, that's correct. And then ARM is a big player. Okay, so if you don't believe me, ARM has a huge market share. So this is a very updated data from 2019, and I got it in 2021. So you can say it's an up-to-date data. So you can say the market share. So mobile application processors, 90% of the mobile phones are using ARM processors. Okay, so we are going to be studying something which is everywhere. Okay, so I hope there is no other motivation required for you to treat ARM processor as your main microprocessor. So 90% is the market share, and they don't want to grow in any further. The remaining may be some other company, but they are dominating, no question about it. Networking equipment, all the routers and all those things, at this point is the 32% in 2019, and they envision that to be 65% by 2028 is what they want. Okay, so you can now
Hopefully no. Data center or cloud, they're not very popular because dominated by the AMDs, then Intels, and of course the NVIDIAs. So they are not really going in there that side. And of course they are dominated by the CISC processors, complex instruction set computers. So but still they aim to have 25% market share there, which is also significant because if you see the number is also less, right? The server or the cloud, maybe the number is less compared to the number of mobile devices that is out there in the market. So by counting that, 25% is a significant market. And then of course IoT application, I don't have to say that because miniaturization is what they play a huge role. 90% is already dominated by ARM. You take any smartwatch, any smart sensors that you will see an ARM processor inside it. I am not joking, you just open up and see there is an ARM processor sitting there. Okay. Manufacture, of course they don't do manufacturing, so it will be manufactured by one of those companies which I listed down in the previous slide. So don't make any mistake there. Okay. And in vehicle, that is one area which they are dominating already. In vehicle infotainment and driver assistance is a huge electronics area nowadays. In fact, with electric cars, you can say it's completely dominated by electrical and electronics engineers. A car, amazing, right? A car is a mechanical device dominated by electrical people. Okay, so it's amazing to see that. So 75% is already dominated by ARM, and they are expecting that it to be 90% by 2028. Okay, so it's not very far, the prediction. Okay, let's see whether it happens or not. Okay, so that's one important thing. So that's why we are going to learn the ARM processor in this course. And then of course heavy usage, because I'm more inclined to tend you to the embedded market because it's a huge area where engineers have a lot of role to play still. So that's my aim, to make you interested in this particular aspect, embedded systems aspect. So ARM is a dominant player, as you can see over from these two cases, right? These three cases in fact. So very cheap to use. So you can say ARM appears to get an average 8 cents per device. That's damn cheap. The board that I am going to literally give you to take home, which is an ARM processor based, which is in fact manufactured by NXP, as I said. So the board is popularly known as Freedom Board. KL25Z is the number for the board. So that board is actually having a Cortex-M0 Plus processor, which is 32-bit processor. It has around 128 GB memory, RAM space, and then it has an accelerometer gyroscope built in. It has so many LEDs for you to test it out, which is also built in. And then it has a touchpad, which is the conventional capacitance based touchpad, which is also built in. And then of course you can interface that with tons of GPIO options, serial interface options, ADC options. So powerful board, and you trust me, the cost of that board is just 1,500 rupees. So you can literally buy that out. Okay, so that's the beauty about this. ARM is very cheap to use. Okay, and then of course it's flexible. I'm not talking about the board after its manufacturing, but the way you can design an ARM processor, it's so flexible. Okay, so that's why companies tend to prefer, and no wonder they're sharing so much of market. Okay, so I hope I am able to make you enough motivation. Now let's have some history of ARM, which is very, very important. So the first ARM processor was developed by a company named Acorn Computers Limited. Nobody might have heard about it. So it is actually out of Cambridge in England, and way back in 1983 and 1985 is where they became popular. At that time, and until the formation of Advanced RISC Machines, that is what the modern day naming of ARM, Advanced RISC Machines Limited. So RISC is nothing but reduced instruction set computers, because their focus is more on reduced instruction set computers. We'll come to that, what is it, you are not aware of it yet. Okay, so later on it was renamed as ARM Limited, but till that time, till 1900, it was known as Acorn RISC Machine. Okay, so ARM was popularly known as Acorn RISC Machine because it was completely owned by Acorn Computers Limited. So this is a picture of the old generation ARM processor. Now you will be wondering why they renamed it as ARM. The history is here. So the company was founded in 1990 as Advanced RISC Machines Limited, the same thing, and it was a structured joint venture. You will be surprised to hear this, between Acorn Computers, the original owners, Apple. Okay, so there's Apple Inc. Now the Apple Inc. And then there is a famous company named VLSI Technology. Google them, you may not find them now, but it got absorbed by some giant players, so you can actually take a look at them as well. So it was a joint venture between these three giant players, and then it was named as this. The reason for this was because Apple wanted to use the technology because they saw that it is very powerful, it is RISC based. Nobody were into RISC business. Intel's or the AMD's or the popular microprocessors, Motorola's for example, were not into RISC business. So ARM was the only company which was into RISC business, and Apple showed or observed the potential in that, particularly with the miniaturization of things and low power requirement of things. They observed that it is important, so they wanted to use the technology, but at the same time they didn't want to buy the entire thing. So it was like a win-win play, right? So you want to see whether it's worth or not. At the same time, you don't want to spend a lot of investment in that. So that's the reason. And just to give you a flavor of it, and sometimes picture picks or sticks in our mind, right? So this is a change in logo as they moved on from 1990s to 2018. So you can see, you might have seen this, you might not have seen this at all. Okay, so moving on. And then what is ARM architecture? Why it is so popular? So as I said, ARM is based on RISC. Again, we don't know what is RISC. We will see that in very soon. Okay, so it's well known for its power efficiency. So power efficiency is something very important, where it is a trade-off between area occupancy and power consumption and the speed of operation. So you tell that you just have a good power efficiency when you have a very good throughput, very fast operation, at the same time very less power consumption or very low area occupancy as well. Okay, so it is widely used in mobile devices, of course, as I said, 90% market share, don't forget that. And then it is designed and licensed to a wide ecosystem. So ARM, what they did is actually any company can come forward, license, get the money, give the money to ARM, get the license of the design that they want, and then they can manufacture it. ARM doesn't prevent them to manufacture. Okay, and it is actually, again, I think this I already told, so you can read it out. I don't need to repeat it. Okay, so now CISC versus RISC. Okay, it is not the RISC. Okay, so complex instruction set computer versus reduced instruction set computer. Literally the name tells you that. Okay, so complex instruction set literally means that your instruction is a very complex instruction. Okay, so it is not like LDA 9H that we did in 8-bit microcomputer. That is a RISC based system because the instruction set is very, very low complex. So when I say complex instruction, literally it means that there is a lot of abstraction in that instruction. So there should be a very complicated control unit to decode that instruction and then make it work. So that is what it means. So program counter, instruction memory, this is all known to you. From that you get a micro program code. So that is something which is like not a very simple instruction. So this is a very complicated thing, and then of course that is actually decoded, and then of course you do all the other things. So you need a very complex control circuit. So everything will become complex. That is the literal meaning of it. So then you will think, what is the advantage here? If you have a complex instruction, your overall program size will become less. Right? For example, I think you do that nowadays very often. So your neural network you take, because all of you are like neural network experts. Right? So you do one line of code in a Keras environment, let's say. So you do a one line of code in a Keras or a PyTorch environment, but you realize that inside that one line you have thousands of lines which is lying abstracted. So that thousands of lines, if you had to write it manually, would have been a terrible, difficult job for you. But then what is the problem? The problem is like you don't know what is inside those abstraction, right? How complicated it is. You may not be able to change something there. Yes, overall size of the program will be like 5 lines. That is the advantage that you get. But the disadvantage that you get is you don't know how this is implemented, how much cost it takes. All those things are like abstraction for you. So that is advantage. The program size will get reduced, but the instructions are so complex that the control is so difficult and so complex that it takes a lot of power, maybe a lot of area maybe, so it's not very power efficient friendly. CISC. So that is why I told at some time in the previous slide that CISC processors are very common in the data centers and the cloud base, where you have a lot of tons of power supply to support you. And maybe I think somebody of you, if you are nature lover, you could say that it will result in a lot of carbon footprint, which is actually a serious problem. Okay, so you are a fan of deep learning, machine learning, you also a fan of nature loving or nature, then you are actually having a trade-off there, because the more complex your deep learning code is, the more power consumption it is going to take, more carbon is going to be released in the nature. So CISC computers are a contributor in that field. Okay, so then it comes to RISC, reduced instruction set computer. Then in this case, this is already known to you. I don't need to explain. Whatever we did is a RISC. So then the instruction is very, very less complex. So your control unit is very low complex. But then the sad side is, like, if you want to write a program, you have a long code to write. So that is actually on the programmer, it is a pain. I think you can understand that, right? I think we will also understand it when we move from the assembly language to the C language. The C language will take only one line of code, where assembly language you needed to program that like 1,000 lines of code, something like that. I mean, I'm exaggerating, but yeah, something in that short. So CISC versus RISC, this is the case. So CISC, again to reiterate, CISC will have, if you are having CISC processors, you can write very efficient programs because it won't take much of space. But then of course it takes long time to perform, it takes a lot of area to implement, control circuit is complex, and optimization is beyond scope. Examples include Motorola 68000, very famous processor in olden days, Intel x86, which all of you are using most of the time. AMD also has something similar. Okay, so it's very, very common to you. Okay, and on the other side, RISC, of course the instruction size is less, so you need to have a lot of patience to write the program in. Okay. Example, ARM, AVR, MIPS, all of them are RISC. I don't know whether you heard about any of them, but it's okay if you don't hear about it. Okay, some of you are into this field, some of you are using Arduino, for example, might have heard about AVR and MIPS. Okay, so let's move on. So I hope it's very clear. So CISC versus RISC should be very clear for you from now onwards, and in fact our Shakti processor was RISC based. Okay, there was a question also in the assignment, and many of you made it correctly, but if you didn't understand that time, hopefully by now you are making a solid understanding of this scenario. Okay, so moving on. So what is that design problem that CISC versus RISC plays a role? So if you are working on a RISC processor, what you care about is this, the cycles per instruction. So because your instruction is very, very low, right? So there is the emphasis is on making the instruction set very low complex, but then the problem is, like, the instruction should get executed in less number of cycles, so that your time to program is sort of not compromised much. So time to program, I think, let me go back to this slide. Okay, time by program can be split into something like this. So you write a program, that program will have so many instructions, but then that instruction will take so many cycles to execute. But then we know that this cycle will take some time to execute. So that's a literal split that you have. And of course, RISC is about smaller instructions. So it is about how fast you can execute those instructions, so that the overall program time is not compromised much. But on the other hand, CISC is trying to minimize this. So you want to actually make such complex instruction that the number of instructions for a program is less. So that is the aim for CISC. So once again, reiterating, number of instructions per program is what the design problem in a CISC architecture, whereas number of cycles for an instruction is the design problem in a RISC architecture. Okay, so objective will change if you are going to work in a company who is designing CISC or RISC processor. Now, so that is all about that generic discussion. Now ARM processor, so we talked about ARM, the significance of it, and some motivation towards that. Now ARM itself actually offers you a variety of designs, right, starting from some classic processors, ARM-7. When I was actually doing my PhD sometime in 2008 to that time, I finished in 2008. So ARM-7 was the default. Everyone was sort of after ARM-7 and ARM-9. Now if you go back and check ARM-7 and ARM-9, it's not at all available, and it is so outdated. So they build after that from there to something like different set of application. So Cortex-M series, M stands for microcontroller series, so they are cost sensitive. Okay, so this is more generic application wise, and then of course used in automotive, for example airbags, so many applications. So M series itself has so many, you can see it over here. So ARM-7, 9, 11 classic, then of course some secure core processors where security applications are the key use case. So then there are three variety of processors there. Then microcontroller series, you have M0, M0 plus. M0 and M0 plus, there's not much change. So even if you are following a book on M0, it's fine. Okay, so it's changed. M1, M3, M4 are slightly complicated. We will see that in the one of the slides later. Okay, and then our processors is real time. Okay, so Cortex-M processors are not for real-time applications. If you are looking at real-time applications, so essentially something like a real-time operating system running on this processor, you have to look at R series. So they are high performance for real-time applications, highly reliable because it has to be real-time. And then of course some applications are this braking system where you have to be really real-time. Powertrain, right? You have to you change the gear, it should be reflecting very soon. It should not be late. Some people can argue airbags also should be there, but we still have some more time for airbag compared to a braking, right? The braking has to be efficient so that airbags get triggered because there is some correlation between them, right? So this is Cortex R series. If somebody tells you that I'm working on an R7 processor, R5 processor or R4 processor, which is listed down here, then that means that they are working on real-time processor or processor from the ARM. Okay, so that's the meaning of it. And then advanced system, application specific, you have so many of them, and they are some examples are digital TVs, smart books, iPads, home gateways, routers, smartphones. They are all A series processors. So you just today this is a homework. You just see specifications of your mobile phone and see which Cortex A series is in your phone. It may be A6. I think it was not A6, A7, which may be very popular. Okay, so we are not going to talk about all these. We are only going to talk about Cortex-M, and even in that we are only going to dig deep in Cortex-M0 Plus. So the essence that I want to tell you is that all these processors, by learning one of them, you will be able to migrate to the another one with ease. Okay, so that is my objective through this course, getting you complete exposure to Cortex-M0 Plus, dedicated effort in that. And by doing that, you are getting expertise in other ARM processors as well. Okay, so this is the design policy. So this is why ARM became so popular. I didn't explain it so thoroughly. So ARM, what they do is they design these IP libraries, intellectual property libraries, not internet protocol. Intellectual property libraries. Okay, so they do design digital designs, they do simulations, they even implement them and test it out, but they don't manufacture as a chip. So they do have this already we discussed. A9, please remember what is A9. It stands for the application level series of microprocessors or microcontrollers. R5, real time. M0 Plus is what we are going to learn today. All classic. So many of them, right? All of them are microprocessors. Let me just point out that. So these are all processing libraries. Then you have the memory libraries, DRAM, flash, SRAM. They are all memory libraries. Then you have interface options. Some of them you will be studying: advanced peripheral bus, advanced high performance bus, auxiliary connect bus. GPIO is a protocol interface. So these are all bus designs. So you will study about them. So ARM does have bus designs as well. So when you say bus designs, is the way they lay out, where they do a digital circuit to make that work, the control aspect, all these things included. And then of course the interface. GPIO is general purpose input output. You will have a session on that separate. Okay. Then input output blocks, timer circuit, etc. So these are all peripheral devices. So you have the processing devices, you have the memory, you have the bus, basically the connectivity, and then of course the interface. So everything is covered by ARM. So they do have IPs, designs which are covered by them. And what you do actually as a manufacturer is you choose some of them. Just like this. So I choose the Cortex-M0 as the processor, okay, and then I choose some RAM, ROM, everything as the memory, and then of course I choose the buses, and then of course I choose the peripheral. Okay, so you made a system on chip. So you combined everything, you pay some money to ARM and get all these licenses, arrange them. That also ARM will help. The layout and interfacing, everything ARM will help, and then you manufacture as a chip. Okay, so single chip solution. This is what you see inside a microprocessor, inside a mobile phone, right? So this is the philosophy that ARM has been following. So they don't do manufacture, they don't do this part, absolutely not, but they help companies like NXP or TI or NI or whatever company you can think about to select based on the requirement some of these. So for example, I will tell an example. If my application is a generic microprocessor, I will go for Cortex-M0 Plus. If my application is real time operation, I may go for an R5 or some other real time series. And then of course based on this I pick and place things and then manufacture a chip out of it. So then it becomes a system on chip. Hope I am very clear. Okay, so there is no confusion. So there's one more slide only, we are stopping. Okay. In fact, 2 more slides. So this again, one more thing. I think there is some technical jargon that I want to explain to you. This part you already saw it. Okay. So basically, there is a fine line. There is something known as ARM architecture and something known as ARM processor. We spend a lot of time on ARM processor, the M series, the classic series, the secure series, the real-time series, the application series is all belonging to ARM processor. So we spend enough time on that. There is something known as ARM architecture also, because this lecture started with that, right? The software hardware handshake. So processor is all about the hardware side. What about the software side? So software side is something like the instruction set, then the memory layout, and there is memory map here, then the register map, for example. Okay, the programmer's model, we will talk about it. Then the interrupt concept and all those things. So these are all something which link the software to the hardware, right? So that is known as ARM architecture. Even there also ARM has a lot of licenses. The way you can, so this is from the traditional way to the modern day. So ignore it if you don't understand. But what we are following is ARM6 architecture, which is used in M0 series. So we will be using that. So but if somebody tells you about ARM processor, ARM architecture, you should be immediately understanding what it means. ARM architecture is not the processor architecture. ARM architecture means the programmer's model. The basically the layout of the registers, the layout of the memory, the layout of the interrupt, or how interrupts are handled inside, what is the instruction set, what all are the instruction set possible for a given processor. So that is the meaning of architecture. Okay, so it is a software architecture, not the real hardware architecture is what they mean. So hopefully it's a small jargon. I just purposefully introduced it here because many people get confused between these two aspects. So if you are talking about hardware, you talk about ARM processor. If you talk about the architecture, you are talking about more on the software side. Okay, hope it is clear. And then of course, I should not end this lecture without talking about Cortex-M series itself, because we are going to dig deep in this guy, Cortex-M0 Plus, and it is a microcontroller series, and some of these things are, I don't want to repeat and bore you. You can read it out and it's self-understandable, and applications you can see. Okay. So, but one takeaway, if I want you to remember something from this slide, is M0 Plus is what you are going to use, but M0 Plus is part of the typical microcontroller series microprocessor or processor from the ARM. Okay, so please remember that. And then last slide, this is the end of it, this week's lecture. So I purposefully not loading you much. You should concentrate more time on the Logisim 8-bit microcomputer, spend a lot of time on that, building that. And this is the last slide. So a comparison between Cortex-M0 to Cortex-M4. Okay, so this is important because we are going to use only this. Okay, so the architecture, going back, this is the not the hardware. The hardware is this processor, so we are going to use the layout which is Cortex-M0 Plus. The architecture, we are going to use the version 6M, which is common between M0 and M0 Plus. So only hardware difference is there between them. Software is same, exactly same. And the core architecture is also von Neumann based. I'm not going to tell you what is it. You should be knowing that, Harvard versus von Neumann. If you're not knowing that, please go back to the lectures and understand that is very important. And then the thumb and thumb 2 is the way the instructions are handled. So you have no idea about them by now, but we will have a detailed discussion as we talk about the instruction set later. So I'm going to leave it till that time as an uncertain area for you. But if you please come back to this slide and understand this when you understand thumb and thumb 2. So let's ignore for the moment. Then hardware multiply. So there is multiplication operation which is very common, right, in our day-to-day life. So in the case of M0 and M0 Plus, you do have hardware multiply, in fact all of them, and there is an option to actually have hardware multiply as a 1 cycle or a 32 cycle. So what is the difference? If you operate in 32 cycle, you will end up in consuming lower power. Okay, so that is the difference. But there is a dedicated hardware multiplier inside all of these actually, in fact. All the microcontroller series. Hardware divide, unfortunately, it's not there in M0 and M0 Plus and M1. It is only there in high-end architectures like M3 and M4. Okay, and no wonder the architecture is also different, right? The software architecture is also different because you need to support them, right? So instruction set is slightly different. Okay. Then saturated math is something which is actually taking care of the saturation of values when you do some operation. That is not there in any of these processors. It's only there in the advanced architecture. DSP, digital signal processing. So some signal operations, something like FFTs, convolutions that you studied in signals and systems course, there is separate library or accelerations available for something like Cortex-M4. Okay, this is not available in any of the other Cortex-M series. It's only available in a high-end Cortex-M4. Of course, the cost will increase. The hardware layout is different. The software layout is also different. That is why you can see there's a difference. In fact, the architecture or the software instruction layout is same throughout M0 to M1. Okay, the only small architecture difference is there, which is actually in this 3 or 33 cycle between these two. Okay, and then of course floating point is not supported in any of them except for the last one. It is an optional service which is given. So this slide is just to give a comparison of where we stand, as our use case is only on Cortex-M0 Plus. We are not very bad, and that's the reason why I chosen Cortex-M0 Plus. We are somewhere which is not bad and which is not exceptionally great as well. And I had a cost constraint in my mind, because literally what I encourage all of you to is to, if you're really interested in pursuing this further, you buy one Freedom board and keep it with you, because it will take you in long stand. Arduinos are old stories, and it's not what good real engineers work on. You should work on something like ARM Cortex-M0 Plus. Okay. So with that, I will wind up this lecture, in fact this week as well. So any questions, keep your emails rolling, or you can put the questions in the discussion forum that is not at all active. So somebody can start a new discussion forum in any of these topics. Again, this is not a very specific lecture. A lot of information is being covered in a very generic way before we really start deep diving into Cortex-M0 Plus, which we will do from next week. Okay, so till then, it's goodbye from my side.